that may have come up in the last half an hour or so? Okay. Okay, so let's start off by looking at the data itself. And what I'm going to do is I'm going to share my screen and I'll show you some example data. Now, the data that I am going to show you is not real. Please don't start copying this down. I will know it. It's just me making up numbers, literally. So it's not real. Let me re-emphasize that. Okay, so you have your absolute numbers, and what I would like you to do is get in a habit of making a nice, clean, organized Excel for each one of your labs so you can keep all the data together and to present it in a nice way. You can attach it as an appendix or as an extra file as well, so I can see your work and make sure I can, give you extra partial credit when maybe there's a mistake, but you were on the right track. So the first thing that we're doing is converting them into percentages. I want you to get in a habit of using Excel formulas to do these calculations and not just your calculators. So we're going to write a formula. So for percent blue, you would need to have your number of blue cells divided by the total number of cells, right? And you want to make sure you put parentheses around that particular portion so that it does that first. And then you're going to multiply that by 100 to convert it into percentages. You're going to do the same thing in the next cell, but this time it's going to be percent clear. So it's number of clear divided by total number of cells and multiply that by 100. So you guys can go along with me if you're at that stage where you can go ahead and do that. Even if you're not at that stage, you can take your empty, completely empty tables once they're copy pasted, and you can do all these formulas in there. And when you populate your numbers, it will populate your calculations automatically. And many times that's what I have is, things that are already partially formatted. And I encourage my research students to do the same. When we design our experiments, we prepare our Excel sheets preemptively, complete with formulas for analysis. So as they get the numbers each day, they just input the numbers and voila, their charts appear. And, that's helpful because then you can start to visually see those results coming up immediately. So yeah, that's what I'm going to do for this particular one as well. And actually you saw earlier that I had it set up that way. That's why this graph is still here. This is still here. When we get those numbers, it's going to start populating it automatically at that point. Yeah. I know I talk a lot, so if I'm talking too much or talking too fast, let me know. I will slow down and go over the material again if you're lost. Now, right now, we're kind of working hard instead of smart. I will show you how we can work smart next time and to get our numbers instead of rewriting the formulas again and again. We will do a little bit of that in a second as well. Clear. So, one of the things you can do, you can just drag it this time because obviously the numbers, the actual places are very different, but you can still actually copy paste and then just change what you need to change within the formula as well. This is one thing you can do. And so I just need to change this portion divided by the total right there. So once I have the formulas for that first column, I can drag it over, whether it's 3 or 100 or 1,000. I could just drag them all the way across and the formula will be copied over. So all your other numbers are calculated automatically. The next thing we're going to do is calculate the averages and the standard deviations. The averages are going to be calculated for either the depth or the viability, depending on your group's overall goal, whether you're looking at the living cells or the dead cells. So in our case, my case, I'm going to look at percent depth. So I'm going to do which ones, blue or clear?
Blue.
Blue, exactly. So I'm going to be focusing on the blue cell since that's what I'm going to be looking at as the depth response. So again, you write the equal sign to indicate that you are doing a formula. And when you start to write average, the function for average formula for that should show up. You click on that, and then I'm going to just select my three numbers. Again, could be 3, could be 1,000, doesn't matter. You select those numbers and click, and you will get them. I'm going to do that for the remaining ones as well. And again, first, actually, let me do the standard deviation as well. For the standard deviation, you can have standard deviation of population or standard deviation of sample. When you're doing just a small subset of the total sample set, then you will do standard deviation of sample. But if you have just a small population to begin with, and you're looking at all of them, then you would do the first one. And that's the one that we're going to select. And I'm going to use the same numbers to select the standard deviation. Now I'm going to go ahead and copy down the formula, but obviously these numbers are not correct yet. I'm going to change them out right here. So one of the things that you would notice if you were to do percentages and standard deviation for both is that you would actually get the same standard deviation, both for your percent blue and percent clear numbers in a particular treatment. Why is that? Why do we get the same number for percent blue and percent clear standard deviation in a particular treatment?
Because the numbers are related to each other. It's from the same sample.
Yes. There are only two groups, right? It's not like there were 3 or 4 or 5 categories. They're just 2 categories within that group. So those numbers are going to be directly related to each other, and you'll get the exact same standard deviation. Okay, so now you have the correct standard deviation. Now I've purposely made this data so that the taxol, if you look at that, looks a little bit different than some of the others. What's that difference that you see?
There's a pretty enormous standard deviation.
Exactly. So what does that show? The enormous standard deviation, what does that show about that sample? About my 3 replicates, what does that indicate?
There's a lot of variation between the samples.
Exactly, that there's a lot of variability. And if we look at those numbers specifically right here, you can see that your percent death is anywhere from 30 to 90%. That's a really large deviation, right? A really large variability. And that's going to affect our statistics, obviously. So even though in all cases you see a lot of death, it still may not show significance in some cases because there's so much variability. And we'll talk about how you can look at statistics in different ways or look at different types of statistics for the same sample set and get very different results. And that's to let you know that you should always take statistics with a grain of salt when you are looking at papers, and actually visually look at the data as well, so that you can see how it really stands? Does it actually show that effect that the authors are claiming that it will have? I'm trying to check for something, 1 second. And then, so let's go ahead and think about what type of statistics we can perform on our data sets. So what would be the most appropriate way to statistically analyze these results? We have 3 replicates in each case, right? We have an N of 3 basically for all 4 samples, and we have 4 different treatment groups, including your control. So what would be the best statistical analysis and most appropriate statistical analysis in this case? Okay. What are different statistical tests that you are aware of that can be used in a research setting or in a scientific data setting?
Student t-test.
There's a student t-test. Good. Anything else that you guys have done before?
One
No.
way.
Nova.
The Anova.
Yes, you can run ANOVAs. What else? I heard of one other test around as well. Something we did back in GB1.
Chi-square.
Chi-square, exactly. Did you say something else, Brian?
No.
Oh, okay. Okay, so yes, so there are many tests that we are already aware of, right? You know the ANOVA, the chi-square, and the t-test. So let's think about the simplest of them all, which is the student t-test. Can we run student t-test to look at the entire data set, all 4 samples together, to see if there is something significant, some different changes in there? Why not? Right?
Because it only does 2 factors, right?
Yes. So the biggest reason we cannot use student t-test alone is because it only compares 2 samples at a time. There's no way for us to compare all 4 as a group and figure out if there is something different in there, right? Something significantly different in there. What about chi-square? That does different variables, no? Could we do chi-square analysis? No, tells me the answer. What do we need in order to perform a chi-square analysis? Does anyone remember the formula for the chi-square? Okay, so if you remember, it's like the sum. It does look at different variables, right? You can have multiple dependent things you're looking at, but the whole premise of chi-square is that you have to have an expected and an observed. Do we have an expected in this case?
No.
No, so we can't run chi-square because we don't have an expected. We only have the observed, what we have. So chi-square is out as well. So that leaves us with ANOVA. And what about ANOVA analysis? What's that used for? Guys are quiet.
Isn't that used for correlations?
Yes, it is used for correlations, and we are kind of looking for correlations, right? We're looking for if we see a particular effect or not. So we don't know what to expect, but we are looking for some correlation between death and the drug treatment, for example, or viability and the drug treatment. So that is something we can use. And Anova analysis can be used to look at multiple treatment groups, not just 2 at a time. So what we're going to be performing is an Anova analysis. Now, these Anova analysis come in many flavors. you have single factor ANOVA, you have two factor ANOVA, and those also can be like with replications, without replications. And then you have what we call multifactorial ANOVA, where you have many, many confounding factors looking at all of them together. The biggest difference between these is the number of independent and dependent variables, okay? So in a single factor ANOVA, you have a single independent variable and a single dependent variable that you're looking at. In a two-factor ANOVA, and those are the two that we're going to be focusing on, the multi-factor ANOVA is a whole new beast that involves a lot of extra calculations. But a two-factor ANOVA involves looking at two independent variables together as well as separately. So it's looking at multiple factors that may affect your dependent response at the end of the day. So for example, if I'm looking at the level of activity or the level of death in response to a particular drug treatment in a particular one cell line or in a particular age group, let's say old individuals, that's going to be a single factor ANOVA. But if I'm looking at the treatment, let's say, some kind of a drug treatment and its effect on mortality or death in young and old individuals, then it's going to be a two-factor ANOVA. In both cases, I'm looking at the same dependent variable, the single death response. But in the first case, I only have one single setting, one single age group. In the second one, I have young and old, so two different age groups, and then I have that response, okay? So in this case, all the data comes from the same cell line. So we just have that one cell line that we are treating. And these treatments, in our case, we're not doing any combined treatments. Two of these are controlled, and these are just considered antioxidant or supplements with antioxidant. So we're going to consider them with the simplest setting, which is a single factor ANOVA, whether treatment with a particular drug is killing it or not, right? You could do them as two-factor ANOVA, but in that case, you're missing a very key, important additional treatment, which would have been black mulberry and saffron together, right? So if we were doing it as a two-factor ANOVA, black mulberry would be one of my factors that I'm treating with. Saffron would be a second independent variable that I'm treating with. And then you would need to have a combined response of black mulberry and saffron together in order to make an appropriate conclusion, okay? So what we're gonna do is just do a single factor ANOVA. Now, the single factor ANOVA by itself is only going to tell you if there is something interesting in that data set. There is some significant difference within the different treatment groups. It's not gonna tell you where that difference lies. To look at where the difference lies, you still need to run a student t-test, which is right here, okay? So what I'm gonna show you is how you can run a single factor ANOVA in Excel, and then how you would run your t-test in Excel. I'll show you two different ways that you can run them, okay? And so I should probably have deleted this, but I didn't yet. I thought I did. Okay, so let's start off with our single factor ANOVA. To run single factor ANOVA in Excel, you need to have the data in an appropriate format. So what you need to do is that you need to organize your data set so that either your three replicates for all the treatments are right next to each other in individual columns or individual rows. In my case, I'm putting all my treatments in that first column, and I'm just putting the data in rows right on top of each other. And these are my three tests, my three replicates, right? 1, 2, and 3. The second thing you need to have is this Analyze Data tab, icon in your Excel sheet. So if you do not see that, if you go into data, oh, not there, sorry. You go into data tab and look for this data analysis tab. If you don't have this particular icon, you need to get that as an add-in. which you can easily do, and I'll walk you through that. For PC users, you can go to File. You would then go to Options right down here. So you go to File, Options, and then you would go to Add-ins on the setting. And right down here, it will say Manage Excel Add-ins and then have a Go button. You will click on Go. A little window will pop open and it will say add-ins available, and then it should have some different add-ins for you. You're going to pick the Analysis Toolpack and Analysis Toolpack VBA and click OK. And that will give you that data analysis icon in your settings. That will give you that additional add-in. If you are a Mac user, it is one of the icons on the top. I think it's Tools or Analysis, one or the other, that you go to, and then you still go to the same thing. You go through Options, and then the same process happens. But just to get to that Options tab, you can't go through File. It's through one of the other bars up there. Okay. Okay. So once you have the data in this correct format and you have your Data Analysis tab, you will click on the Data Analysis. It's actually going to be the very, very first one that you need to run. It's Anova single factor. Now, Anova, and we will run two-factor Anovas later. Two-factor Anova can only be run with exactly the same number of replicates. Both t-test as well as your single-factor Anova can be run with unequal numbers of replicates. So if I have n of 50 in one and n of 25 in the other, it's not a problem. But in two-factor Anova, you can only have the exact same numbers. So to count, to counter for that, it allows you to do either a two-factor with replication if you have equal numbers of replicates, or you can do two-factor without replication, where you just take the averages of the numbers and use them to run the Anova. Obviously, this is not going to be as accurate when you do it without replication, but it gives you a general idea. So for now, we're doing single factor. You're going to click OK. It's going to open a box and it will ask you for your input range. You will select all the samples that you've got, right? And all the numbers that you have in each of the samples. So you want to select the column with the name of the treatments and all the numbers. And in here, you will say, well, the data is grouped by columns, yes. And the labels are in the first row. Well, in our case, the data is grouped by rows and the labels are in the first column. So make sure that you select for that. And then you need to tell it where you want to see that data. I always tell students to put it on the same sheet as the data itself. So you just find an open, nice, clean spot and select a well there so it can put the data and cell there so the data can go there. And then click OK. And it will provide you with those numbers. Now, once it gives you, the first thing you want to do is make sure it has done it correctly. So there should be no just, number or something written and no information written. You, in the summary form, you should see all your 4 groups. So untreated, positive control, black mulberry, and saffron. You should see the same number of replicates as your number of samples. We had n of 3. It says count as n of 3. That's great. And your averages should match up. So 3.6, 65.2, they look the same. Good. Got it? And then it will give you the variance of the samples as well. Obviously, the positive control has a lot more variability, and that's shown right there. Underneath will be the actual Anova results. You will see the F critical and the P value and the F value. So right now we are going to be focusing on the P value specifically. So right now the P value says it's 0.009. Is that significant? Yes or no?
Yes.
Why? What does it show and why?
Because you want a p-value below 0.05.
Yes, so the p-value to look for is 0.05 or less. What does that 0.05 indicate? Why is that so special? I'm going to go ahead and highlight it since it is significant. That shows that there is significance, so you can easily spot it. But why is that 0.05 so number so special? What does that mean? Any ideas? Any just like guesses? How about guess?
Does it account for the 95% confidence interval?
Exactly. That's exactly what it is. It's what we call a 95% confidence interval or a 5% false discovery rate, 5% FDR. So there's only 5% chance that this observation is just incorrect or not correct for its significance, and 95% confidence that the observation we're seeing to be significantly different is in fact true correlation. So that's why we look for that 0.05. Now, as we increase the number of samples, as in the number of treatments, that number actually statistically goes to a different number. So there are corrections that we sometimes have to make for those additional treatment groups, and that may bring it down to 1%, that your FTR has to be 1% to be significant or 2% to be significant. However, for simplicity's sake, we're just going to keep 0.05 as our main thing for now. Okay, so now this just tells you the significance. It doesn't tell you where it is, so we need to find it. And we need to find it by doing what we always do, t-test. So we have to run student t-test where we do pairwise comparisons between all the groups. So you're going to compare untreated against all the other groups, including your positive control. You're going to compare the positive control with the other two treatments, the black mulberry and saffron, and then you'll compare your black mulberry to saffron itself. And all the pairwise comparisons basically will then tell you where exactly the significance is and how important it is, how significant it is. Got it? So to do the easy version of the t-test, or quick and dirty version, you do again the equal sign, you look for the t-test. It's going to say what do you want to compare. So you're going to compare your positive control against your untreated, right? And then it's going to ask you if it's a one-tailed or a two-tailed distribution. So do we know which way the positive control is going to go? Do we know whether it's going to show death or not? Yes or no? Brian is nodding his head. Anyone else?
Yes. Yes, we think it's gonna be-
Yes. So Brian, I can see you, which is great. Otherwise, you could be nodding all day. I wouldn't know. But yes, in this case, we do know what to expect. So we can choose the one-tailed distribution. If we didn't know, we would have to choose two-tailed. If we didn't know whether it's going to increase or decrease viability, we'd have to do a two-tailed. But we can do one-tailed in this case. And then it's going to ask, is it a paired sample? Is it two sample equal variance or two sample unequal variance? Now in Excel, you can run the F test and variance test to look for variance as well. You can look at variance right here and see that they're very different. So here it's going to be, it's not paired. Paired samples would be where they're either, the same cells that you take before and after treatment, or essentially the exact same background, exact same everything at different time points after treatment. And this is not that. So these are two separate cultures. So we are going to do 3 in this case, to sample unequal variance. And then you would select enter. So you can see that this shows a 0.04 as your number. Does that show significance? Yes or no? It's below 0.05, so it does show significance. Oh, wrong one. Oh well. Up here, let's change that to yellow. There you go. Okay, so now let's do one of our treatment samples. Do we know what to expect in them? Yes or no?
No, because that's what we're testing.
That's what we're testing for. So for those, you still do, your black mulberries compared to the untreated. But now I don't know which way it's gonna go. So I have to do two-tailed distribution. Again, it's gonna be the same unequal variance and close. And you do that. Does that show significance?
Yes. No.
It's
Yeah.
0.078. So no, it doesn't. It's above 0.05, so it doesn't show significance. Let's do one more, and then I'll show you something interesting about our data, because I made it that way, unfortunately, or fortunately. And again, it's going to be two-tailed and 3. And this one shows 0.017. Is it significant?
Yes.
So even at this level, you can see that compared to positive control, this shows more significance because this had less variability in the data, right? And if you had done the same test using the same criteria as where we did two-tailed distribution, you wouldn't have seen any significance at all because of the variability. Even though it's like 90% and 78%, 27%, they're all, there's 2 of the numbers are way higher than any saffron shows. It wouldn't have shown significance because the numbers were so variable. Now, if instead this number was a 72, right? Suddenly the significance goes way down, right? It becomes way more significant. The p-value goes way down just by having the numbers more closer to each other. Yeah. So just because you see a really large response, sometimes you still don't see the significance. And just because you see significance doesn't mean that there is a response, because a researcher can easily, instead of, tweak the data in the way they want to show sometimes. So you always have to look at the actual data and see if that response does in fact show the conclusion that the researchers are telling. Cool? Yes? Okay.
Yes.
So these are the statistics that you're going to perform, and these statistics, the tables are going to go not here, but up above where the tripe and blue data was. Oh, come on. Right here. So you're going to put that table, the t-test table and the Anova results right here. Okay, so you can simply copy them. And you can put them in here. You can put them as a table, or you can put them as a, Excel just embedded sheet. So just copy paste it. And above this, you would write table 1, and then the title would be in bold, which would be, whatever the main point of this table is, title in bold. And then your caption in front of it, detailing what is shown in normal text. Single space. Got it? So tables get a title and a caption above the table, Figures get it below, and tables get above. So that's what you're going to do for this one. You're going to write a detailed caption in front of it. Basically, it's going to say that, you're comparing those 4 groups with n equals 3 per group. and you're looking for significance, and it does show significance since the p is less than 0.05. And the second table that you would have in the same thing would be the t-test, because you have to show those as well, right? So again, you would just copy, paste that table in there and write a title and a caption above. Cool? Questions about the table portion? Before we go on, and our statistics, before we do our last part, which is morphology. So that would be table 2. Okay.